Okay, cool. Hi, everyone. We're going to get started. Can I actually ask the people that are sitting in the back to come move up to the front? I would greatly appreciate that. Thank you. Okay, so I'll start with the audience. I am not Sylvia. My name is Alex. I'm one of your TAs. And for the second flipped lecture, the TAs got together and we thought it would be nice to give you a lecture from the perspective of someone who took the class recently and went through the material recently, and talk through some of the things that we found confusing when we were learning this material not too long ago. So, yes. This lecture was prepared by me, Narek, and Sarah, so two other TAs. I happened to take 168 here some years back, and they took the equivalent at their undergrad institutions, and so that's what we're basing our content on. So I'll start with some announcements. One, starting this week, in-person lectures are back. So no more videos to watch before coming to lecture. And Sylvia will be lecturing. Me being up here is a fluke, just for today. And two, the other really exciting announcement is that Project 1 is released today, immediately after lecture. And I'll share some more information about this project. You're going to be implementing a distance vector routing protocol. And in particular, what makes this really fun, why I like this project so much, is you'll be working with a simulator that Murphy McCauley and past grad students in NetSys have written, where you'll actually be able to see exactly what is happening in the network. So I have a little video from when I was working on this project over the weekend. It's very fun. The simulator is all jiggly. You can move all the nodes around. You can see all the packets as they flow. You can send packets from some host to another host. And you're going to be responsible for building the routing tables to make an arbitrary network function, which is really cool. So the project is split and scored by 10 stages, and the goal is going to be effectively to derive each of the changes that we learn to distance vector, optimizations to distance vector, starting from just basic packet forwarding and then understanding why we need things like split horizon, poison reverse, route poisoning, et cetera. It's going to be due at midnight on October 7th. And all of the information is going to be on ed at 12:30, immediately after lecture. Okay? And as people come in, just if you can come and sit in the front, that would be great. Thank you. I'll just also give a shout out here to Silvery, Tenzin, and Ken, who are the project TAs for this project. And they've been working really hard to get this ready for you and to get it released. And they will be the ones supporting you. So this is important. If you have questions while you're working on the project, come to project office hours, not the content office hours. So they specifically have lots of project office hours to get help. Are there any questions about this project release? No. Cool. I'm actually going to start with a few tips briefly that you should think back to as you start working on the project, just because I was just working on this project and from when I took it in the past. Given that the project is made up of these stages, later stages are going to require you to go back and edit your earlier code. So I highly recommend that you comment your code in the earlier stages because you'll have to go back and edit it. And very quickly we forget what our code does, even though we just wrote it. Very handy. Remember that when a node receives an update, if you are told that your neighbor has a path to some destination with some cost x, your path to that destination, if you choose to use that route, is x plus your distance to that neighbor. So you have to keep track of, you take however far your neighbor is from the destination and add your own distance to that neighbor to get the total cost that you store. And that was just something that bit me when I was working on this. And a higher level comment to say that this class doesn't have that many assignments, right? We have 2 projects, one kind of homeworkish thing that'll happen later in the semester, and 2 exams. And so this is your chance to really get very comfortable with these concepts of split horizon, poison reverse, and route poisoning, and how distance vector works. Because when it comes time for the exam, that's where we're going to apply these concepts and kind of stretch them more. And so really make sure for each of the parts you understand why what's happening is happening. And if you just follow the PDF, the instructions, it has questions to help you understand, as long as you make sure you're taking the time to answer those questions for yourself. Something that helped me do this is when I was thinking through things, I logged what was happening. So whenever I was writing an update to my table, the routing table, I would log that I was doing that, and then I could really look at the sequence of events and try to understand why the sequence was what it was. So And my last tip for you is that the simulator is a Python terminal. It's interactive. And so actually, while the simulator is running, while you have that little visual section, you can also refer to each of the nodes by their actual names, like S1, and view the routing table live. You can do print s1.table, and it'll show you the exact innards of your routing table. So that's really handy for debugging what's going wrong. OK. If there aren't any questions about the project, then I will get started on the section of lecture, what I found confusing about routing, and hopefully how we can clear it up. OK? So every semester, students get confused about this. They get confused about all these new terms, split horizon, route poisoning, poison reverse. And in particular, I see these questions very frequently. People ask, what combinations can you use? Which one of these three is the best? What is route poisoning versus poison reverse? The naming, the fact that it's so similar, doesn't help. Of course, even within split horizon versus poison reverse, what are their differences? So let's take the time today to clear those up. I'm going to set the stage first to remind you, this has already been talked about in lecture, but why are we doing this in the first place? So the core problem that we're trying to solve with routing is coming up with the rules for how we're going to forward packets. So as a router, you get a packet, you look at the header, and your job is to decide, to get this packet to where it needs to go, what do I do with it? Which neighbor do I give it to? Routing as a problem is how you come up with those rules, so that the actual decision-making process of who I should give this packet to, defining how you make that decision. And you have to make these decisions with some sort of requirements in mind. In particular, two very reasonable requirements. You probably want full connectivity, meaning that as long as a host is part of this core connected component of the graph, as long as it's theoretically reachable, it should be practically reachable from any part of the network. And two, you probably want to minimize latency. So get to your destination as quickly as possible. Don't take some very convoluted route. Take the shortest path to the destination. I'll point out, this routing is happening in the control plane of the network. And so really the function of our network is broken up into two pieces. We have the data plane and the control plane. And the data plane is the actual process of you get a packet, and you're going to look up and give it to a neighbor, the actual process of handling that packet. The control plane is making a decision of how you're going to handle that packet. So to which neighbor you should give for a particular destination, that sort of decision making is part of this control plane. So far we've been talking about link state and distance vector protocols as two of our approaches. I don't necessarily find link state easy, but I find distance vector harder because we start off with some general set of rules and we add these little optimizations to kind of make it function better and better. And so, especially because our project is focused on distance vector, let's talk about distance vector today and save link state for another time. So if we have time at the end, I'll take questions on that too. So what do we do for distance vector? It's two simple rules. One says every node is going to tell each of its neighbors its distance to some destination. Okay? Yeah, as a speaker. And so R1 is going to tell all of its neighbors, which here happens on the screen, just happens to be R2, hey, my distance to D is 1. R3 is going to tell R2, hey, my distance to D is 15. And by the way, where does that 15 come from? Well, maybe there's kind of a path off screen here, down below, through some more convoluted part of the network that eventually makes it back up to R1 and to D. And so as speakers, every node is going to tell all of its neighbors its distance to some destination. And then as a listener, every node takes in all these updates and decides which of them it should use, which advertisement it should use for its route. And that should be an easy decision. A cost of 1 to get to the destination is better than a cost of 15. And assuming that R2's cost to R1 and R2's cost to R3 are both the same, they're both 1, we should take the shorter route. What are some problems that we're going to run into? Well, generally, our problems in the network are caused by some sort of invalid network state. And so I'll actually turn to you and say, what are possible sources of invalid network state? What are issues that we can run into in the network? They're going to cause us to not route optimally. Yeah. Yes, we do have problems with links going down. I agree. And what's the result in the actual routing state? So in these tables that we've built, what happens? Yes. Yeah, I agree with that. You get state where someone thinks something exists when it doesn't exist anymore, and that'll be a problem. Someone else had their hand up, I thought. No? Okay. Any other problems you can think of? Yeah? Ah, yes, looping. So we can get into this unfortunate situation where both nodes think that the other has the shortest path to the destination. And then when they get a packet, they hand the packet to each other, and the packet goes back and forth. And that's a problem. I agree? Yeah. Yeah. Yes. And in particular, that does happen when we get some sort of kind of looping behavior where I tell you I have a path, then you tell me, no, I have a path, and we go back and forth until we count up. These are all problems that we'll run into, yes. This is great. So I've kind of written these down for us to walk through, and I framed them in these three groups. The first, I'll say missing entries, and what I mean by that is, no one really mentioned this, but for completeness sake, it is a slight problem if there does exist a theoretical path to some destination, but a router doesn't know about it, right? So there is some host that it's attached on the other side of the network, but I, as a router, don't have a path to it, even though it's theoretically reachable, and that's a problem. And we'll talk in a second about how that problem comes to exist. Then someone else mentioned loops, and this is exactly a problem. We can get into a situation where two routers think that they are each other's next best hop, but in that case, the packet's never going to make it, and that is a problem because we now have lost kind of from that. Starting from those nodes, you can't get to your destination. And finally, I think you mentioned this stale network information, where not everyone knows about a failure that's happened. So, drilling into these missing entries, what might lead to this happening? If every router is following these two rules for distance vector we just talked about, and they're all honest, and so they're going to tell their neighbors what their distance is to destination, how would it be that not everyone knows? Any thoughts? Yeah. Right, right. So remember, we have this issue of our underlying network is delivering best effort. Some packets can get dropped. So you have this problem where you could tell your neighbor, but your neighbor might not hear it, not because they're ignoring you, but because the packet just doesn't make it. So that's definitely an issue. Advertising gets dropped. I have another one here for completeness, which I think is a little unfair. Just to say that maybe the destination is actually unreachable in your topology. Like a link goes down to some destination, or it's kind of not part of one overall connected component, and I just have it here for completeness. How do we solve this advertisement getting dropped issue? What was it? Yeah. As long as we resend every certain number of seconds, right? As long as our link is not always dropping packets, it has some % chance of making it, then if we just keep retrying, eventually the packet is going to make it. And so that works really well, actually. We just retransmit every X seconds. However, if the destination is unreachable, there's not really any fix for that. Whoops. Your only option is to get the network connected again, and so that's not really something we can fix with routing. So cool. This first problem, we have a solution for. We're going to retransmit advertisements. But what do we do about looping? This will be important. In particular, can anyone give me a kind of a succinct description? What causes a loop? I mean, how do we get into a loop? Or once we're in a loop, why are we in a loop? I think said something very similar to this earlier. Yes. Roger. Yes, so I think you're answering the question of, hey, how does this how do we stay in this loop? And even mechanically back and forth, why do we accept updates? All very true. I was looking for even more broadly, a direct loop means that I think that I should give my packet to you, and you think that you should give your packet to me. So we have forwarding tables that kind of point at each other. That's very unfortunate. And so how do we actually get into this scenario? Well, imagine you have a network like this. And here, this is all valid forwarding state where to get to D, R3 thinks I need to give my packet to R2. To get to D, R2 thinks I need to give my packet to R1. And R1 is directly connected to D, so this will work. But we run into an issue where if a link goes down, well, eventually, R2 is no longer getting updates from R1. And so its entry is going to time out. But R3 is going to advertise saying it has a path to destination. That advertisement comes in, and R2 is pretty happy about that because it no longer has any way to get to D, and so it's very happy to hear that R3 does have some sort of way to get to D. So great, R2 accepts that, says my next hop is R3, the path of cost of 4, which was the cost of R3 plus the one hop cost to get to R3. And unfortunately, this is just going to go on back and forth. They're going to keep passing these updates to each other and updating the costs, counting all the way up to infinity. So I get to 6, to 7, to 8, and this continues forever. OK, now finally we can get to talking about what the confusing parts were for routing for me. Specifically, this is the class of problem, or at least how I think about it, of what split horizon and poison reverse are attempting to solve. We're trying to prevent loops from happening. And if they do come up, making sure that we get rid of them as quickly as possible. So split horizon comes in, and the rule with split horizon says, if I have a route through you, I will not tell you about my path. I will not tell you about that route. Because why would I ever tell you about a route that goes through you? If I tell you about it, you shouldn't ever have to use it. If you do have to use it, we're in a loop. Because if you give me a packet, I'm going to give it right back to you. And this sounds pretty good. I mean, in fact, if we walk through what happens here, same link goes down, same forwarding table entry times out, but then D is just not going to say anything. Sorry, R3 is not going to say anything to R2 about its path to D. And so eventually, R3's path times out, sorry. And now we're in a state where neither R2 nor R3 has a route to D, and hopefully someone else in the network sends an update to R2 or R3 saying they have a path to D. And at that point, we can accept that new path, and our network can reconverge. Hopefully, that's what happens. Does this work? Yes, everything works sometimes, yeah. It's a safe answer. Does anyone have a more opinionated answer? I mean, I think it works. It should work, yeah, ideally. So it does work in the sense that you can't really have a direct loop form in this case. But there are still edge cases where you do get loops, direct loops forming. You saw one in a previous lecture that Murphy did, where there were two routers talking to each other that had a path through some third router. They both went through the third router. When that third router went down, if the timing comes out just right, where R1 and R2 tell each other about their paths through that other router, and the routing entries expire at the same time, you can get into a state where they are now sending packets to each other again. So there is this edge case, and you'll see it very closely on the project. And so split horizon works to prevent many kinds of direct loops. but there are still edge cases where they can come up. And what happens in those edge cases? So let's say that with one of these edge cases, we get into this scenario where R2 wants to give its packet to R3 wants to give it to R2. Split horizon does get us out of this issue where R2 is not going to tell R3 about its route, and R3 is not going to tell R2 about its route anymore, now that they're pointing at one another. And so eventually, the two entries time out. But we have to wait an entire time to live. So the entries actually have to time out. And remember, TTLs are like usually considerably greater than advertisement time. And so we're in a loop for a little bit of time. So this is where poison reverse comes in as an optimization. So it's an improvement on split horizon. And it says, actually, instead of just being silent about my path through you, I'm going to actively tell you that I have an infinite cost path. Okay? So if I'm going to route through you, I'm going to tell you I have an infinite cost path. And often you'll hear this talked about as lying. Why is this conceptually lying? Because you do actually have a path that is less than infinite cost, but you're going to say it's infinite cost to make sure that in no world is your neighbor going to give you a packet. Yeah? And all routers, like who's going to send a packet on a path with cost infinity? And so what happens is, assuming we somehow got into this state, you can trust me that there are these edge cases you'll see on the project. Once we're in this kind of looping state, if R3 is going to send an update to R2 saying that its cost to D is infinity, and R2 has to accept that, by the way, right? Someone pointed this out earlier. You might wonder, well, whoops. Well, why is R3 going to accept a path with cost infinity when it has an entry with a cost of 2? Well, it's because that update is coming from R3, which is R2's next hop. Right? So as soon as your neighbor says, you have a path through your neighbor and they tell you their cost has gone up, you have to accept that because that's newer information, that's better information, and what you have is outdated. And so that gets set to infinity. R2 is also going to tell R3 about its path through R3, saying it has a cost of infinity. And so very quickly, both entries are now no longer used. Does that make sense of how we get out of this scenario? I just want to really highlight, we're getting out of the scenario in the amount of time that it takes to send a new advertisement. We don't have to wait for anything to expire. So that's already an improvement on split horizon. So to really concretely answer this question of what is this difference between poison reverse and split horizon, mechanically I've showed the difference. But intuitively, they should be preventing the same kinds of direct loops. They're both equally good at preventing. But in the case where we do get into a direct loop that they don't prevent, poison reverse squashes those loops much quicker than split horizon. Because you actively tell your neighbor through whom you're routing that you have a cost of infinity, so don't ever send me a packet to that destination. Yeah? No, I think when we actually implement this, if you have a cost of infinity, you don't send along that cost. But even if you did, I mean, the point is that if the destination is actually reachable, someone else's update will come in, and if anyone else has a path, it's going to be less than infinity, and so you're going to take the route through someone else. The problem is, while you still have your old update, I'll just point this out. This is a good question. While you are in this state, if someone else tells you, oh, I have a path to D with cost 6, you're not going to take it because you still think that R3 has a path with cost 2. So the quicker we can change that to say infinity, the quicker this router is able to accept updates from other neighbors. Yeah? One downside to split horizon is that to poison reverse is that it's chatty, right? It's going to send it's going to send this infinity instead of being quiet. But the difference is negligible in the amount of traffic we send. So no, I don't think I can think of a reason. Yeah. Any other questions? Okay. Cool. Okay, fun aside, can anyone guess why it's called split horizon? I was able to find this kind of cool picture of an actual split horizon on Reddit. Reddit has everything. Yeah. Okay. Yeah, so it's like by breaking a loop, you're having the two neighbors take other paths. That's a good guess. No, but I like that. Any other guesses? Yeah. It's a what? Like a boundary between the two neighbors, they don't talk to each other? That's also a cool guess. No. Okay, I'll reveal it. I looked this up, and in the original paper, they describe like the forming of an update of like all the paths that you have is kind of your horizon. And I imagine it's like you're a node in the graph, and you look outwards, and I guess that's kind of like your horizon, like how you get to everywhere else. But specifically, it's split because you're omitting information to a particular neighbor. And so different neighbors are getting kind of different views of your horizon. Particularly, the neighbor through which you're going is getting you leave out the paths, the routes to destinations that you use that neighbor for. And so each neighbor is kind of getting a different overall view of your horizon. The paper also describes this term as a whole horizon, which is like without split horizon, if you're sending everything, it's called whole horizon. We don't use that in this class, but it's kind of cool. Okay, we've solved our looping problem. That's great. Yeah.
Should we be implementing both split horizon and poison reverse just as a backup?
It's a good question. Let's think through that. How would we go about implementing both split horizon and poison reverse? So what does split horizon say to do if you have a route through that neighbor? Don't say anything. What does poison reverse tell you to do if you have a route through that neighbor? Say something. You cannot do both, yes. Right, you can't both say nothing and say infinity. You have to do one or the other. Yeah? Yeah, we will. But this is as we're deriving kind of step by step as we get kind of cleaner and cleaner solutions. Okay. So let's deal with this last problem that we identified. Stale network information. So how do we get into the state? Any change in the network state is going to be an issue for us, right? It takes time for this information to propagate through the network. And in particular, I'll point out that different classes of information take different amounts of time to propagate. And so these are terms that, I don't think Sylvia uses in this class. I just have painted it this way of kind of like additive information, like someone comes up. So information that you didn't have before, new information, versus subtractive information, meaning information that people had that now needs to be revised or removed. And specifically, additive information propagates as quickly as the advertisement frequency. And that's relatively short. We're going to be, because we want to resend updates, we're sending quite frequently, much quicker than the time to live. Subtractive information, so information gets removed as quickly as it can expire. And that's always longer than our advertisement frequency. And so in particular, we get this issue with information about a router crashing, or a link going down, or hosts being disconnected. Once someone has told you about this, that's not going to get removed from your table until it expires. So what can we do to improve this propagation time? So this is the separate kind of slightly orthogonal problem that route poisoning is trying to solve. And the key observation that we saw with poison reverse was you can override a neighbor's time to live, right, by sending an advertisement that has infinite cost. So rather than waiting for someone's information to expire, you could actively tell them, this information, this host still exists, but the cost is infinity to get to it through me. And so we're going to take advantage of that to try to get to a place where we converge more quickly, where information spreads to the network more quickly. So now with route poisoning, the rule is this. When you lose a route for whatever reason, instead of just deleting it from your forwarding table, tell all of your neighbors that your distance is now infinity. And the rule should make sense. You want to actively tell other people that now you can't reach that neighbor anymore. And try to update their tables with the cost of infinity. And so we can, we can walk through a case here where we had our valid setup here, R3 sends to R2, R2 to R1, R1 to D. And unfortunately, this link goes down. So R1 to D goes down. And R1, these host links is going to detect it. And so it sets its cost to infinity. Well, following route poisoning, R1 is going to advertise that infinity to R2 to let R2 know that it has a cost, that R1 now can no longer reach D. And then D is going to update its table and say infinity. And R2 is going to update its table to say infinity to D. And now R2 is going to advertise to R3 and say, hey, my cost to D is now infinity. And that's going to continue onwards. And I just would point out, you actually kind of get this for free in the implementation, because as long as you just store infinity in your table, if you were to remove the entry, well, by storing infinity rather than removing the entry, at the next advertisement period, your code by default is going to advertise infinity to the next neighbor. So you'll notice in the implementation, depending on how you implement earlier stages, when it gets time to implement route poisoning, you may not actually have to change much. Any questions on route poisoning? Yeah. Sorry, the next advertisement frequency, is that what you meant? So the question is, why should we even wait until the next advertisement frequency? Why don't we send right away when we hear about infinity? And in fact, that'll be the final optimization where we're going to say exactly that. Why should we even wait till the next advertisement period? Let's just talk immediately when we find out about bad information like that. Any other questions? Yeah. That is a great observation. So in this particular case, because it's kind of to the host, remember that hosts don't participate. They're not like speaking or sending updates. So someone went in and like hard programmed a static route that has a TTL of infinity from R1 to D for the direct next hop. And so R1 needs some sort of method to tell that it's linked to the host went down to update that cost infinity. If, however, it was a link between two routers, then yes, you would have to wait for that initial TTL, like the time to expire. And after that, things can propagate as quickly as advertisements. That's a great catch. Other questions? Yeah. Yes, how is this different than poison reverse? Let me come back to this in just a second. I have a slide on exactly that comparison in just a second. So we now have a solution for our third problem, more or less. Now I realized I just wanted to point one thing out that I had on my slide here that I forgot to say earlier. Split horizon and poison reverse, they really help us with preventing and squashing direct loops. Meaning a direct loop is where I give my packet to you and you give that packet back to me. They're not used for handling cycles, where I give my packet to you, you give it to someone else, and they give it back to me. So we actually need a different fix for those kinds of loops. Just point that out. OK, so we had, whoops. These are the three questions I listed earlier that were always confusing to me, and I find students get confused with easily. What combinations of these can I use? Which one is best? And route poisoning versus poison reverse, which I'll have a nice chart for. So which combos can I use? Well, luckily this came up as a question earlier. You can't use split horizon and poison reverse at the same time, because they conflict. One says, say nothing, and the other says, say cost infinity. And so your options are, for these two classes of problems, pick one of these solutions or none. And so to be kind of really precise or pedantic, these are all the options you have, where you pick either split horizon, poison reverse, or nothing, and route poisoning, or nothing. You don't need to write these down. You don't need to memorize them. This is just to point out these are the combinations that are possible. And to put it succinctly, something from that set on the left crossed with something from that set on the right. The other question I see people asking is which one is best? And I think there are different tiers to this question. Some people are asking which combo is best, but others are asking actually of the three, which one is the best? And I think it's a slight incorrect assumption when you ask that, because you can't compare all three. Split horizon and poison reverse address one problem. Right poisoning is kind of addressing a different orthogonal problem. And so maybe the better question is what combination of them is best? And to put it shortly, better to use some strategy to solve a problem than none. And it's just rat poisoning or nothing. And for loop prevention, poison reverse was just as good as split horizon, but when loops do arise, direct loops arise, poison reverse squashes them more quickly. So I'd say poison reverse and rat poisoning are the best combo. Finally, for comparing rat poisoning and poison reverse, what is the difference? So they are solving, at the end of the day, we're all trying to decrease kind of convergence time, how quickly our network gets back to a valid state. But in my mind, they're kind of solving slightly different problems. And so while their mechanism is the same, of sending infinity, they're triggered by slightly different things. So poison reverse says, if I get an advertisement from my neighbor that has a lower cost than me, than what I currently have to get my destination, I will from now on tell that neighbor that my path to that destination is cost infinity. So I'm going to lie to that neighbor, and only to that neighbor, no one else. Whereas route poisoning says, if I lose a route altogether, not that my route got replaced, but that I lose that route, I'm going to tell everyone immediately that I no longer have a route to this destination. Does that distinction make sense? And so even though they're both sending infinity, they're also doing it slightly differently. For route poisoning, you send infinity to everyone around you to that destination, because you actually have no path to that destination. For poison reverse, you're only going to tell the specific neighbor that you have a route through that your cost is infinity. Everyone else you tell the truth to, whatever that cost is. Does that make sense? Okay. Now, for a split horizon versus poison reverse, I'm going to show one more kind of top-down view on a network that maybe will help you visualize what's going on here. These are from Murphy's slides from an extra little slide deck that he made. We have this network. It looks like this. All of our edges have cost 1, and for now, let's just focus on one destination, because conveniently, as we think about all these things, additional destinations are just more layers of messages on top. The core principle is we can tell with just one possible destination. If we were to look at the best paths to A, that tree would look something like this. And how do we know that these are the best paths? Well, you can just kind of verify that the shortest possible path from 10 to the destination is 1, 2, 3 hops. There's no better path you can come up with on this graph. You could say, well, like, why does 9 go to 3 instead of to 5? That might be an equivalent best path tree, but we break ties consistently here by saying we're going to take the neighbor that has the lower ID. So in a world without split horizon or poison reverse, let's just focus on our router switch 1 here. When switch 1 goes to advertise, it's going to tell everyone it knows, everyone in the world, that it's connected to like each of its direct neighbors, that it has a path to A with a cost of 3. Everyone hears about that. Everyone who is connected to 1 directly. In a world with split horizon, it's still going to tell all of its neighbors, but it's going to be silent to 3 specifically. It won't say anything. Yeah? And in a world with split reverse, it's going to tell everyone, but it's going to lie specifically to 3. So instead of sending nothing, it's going to send, I have a path, but it's cost infinity, so you better not give me any packets. And so if you just kind of step back and take a look, these are all the advertisements that are not sent due to split horizon. And for poison reverse, it's the same exact kind of edges that aren't sent, but instead of not sending, we send the cost infinity. And I'll point out, this looks very similar to something. In fact, this looks identical to the best path tree that we had at the beginning. This should make sense because you don't send your updates along the route that your packet is going to take. And so the updates that you leave out for a split horizon, or the updates that you send with a cost of infinity, they will be on the same edges as your best path tree. Kind of look from above. I'm going to cover one more quick topic that I found confusing. I have like 2 slides on this, and then we'll take a break. And then we'll switch over, and Narek's going to talk about Spanish tree protocol. So one other thing I keep seeing people ask, and I wondered this for a while too, was it seems like we need to do routing for both L2 and L3. So which should we be using? We've learned about distance vector. We've learned about link state. We're also talking about learning switches. So what should we be using? Well, L2 is responsible for local packet delivery, and L3 is responsible for global packet delivery. And so the routing problem looks a little bit different in each of these domains. So how does it differ? Well, they both have the same kind of goal of a shortest path and to be resilient to failure. But L3 is a potentially very large network, whereas L2 is all destinations, focused on all destinations in a smaller local network. And it's more plug and play, where people in your local network are going to bring devices, move devices, with minimal support. And so L3 has this property where it has to be scalable. There's this whole question of addressing and how we handle addressing. Whereas L2 is you have a small network, and it needs to be operated with lower cost and like lower setup difficulty. And so we find that distance vector and link state are a better fit for L3, where they scale well, but they require some initial setup with addressing, which gives us some sort of static configuration. Whereas with a small network, we can use learning switches, which initially flood a packet, and Narek's going to talk about this in a second, and then learn routing after packets get flooded, as we see packets fly by. And so learning switches are a much simpler solution. There's less setup involved. They're a good fit for L2. Distance vector, length state are kind of heavier, and they're better for, they require a little bit more configuration, and so they are a better fit for L3, for a larger network. Yeah? Well, for one, so far up until now, you've had to configure your like attachment to hosts directly, right? Like a network operator had to come in and say, you as a router, you have a direct link to this node, and fill in that table, and then let that propagate, for example. Whereas with learning switches, people learn that they're connected, who they're connected to, once someone speaks. Yeah? Yes. There isn't a separate protocol where learning switches are talking to each other. They are learning from actually seeing the data flow by. So if everyone's silent, they're not learning. Before we go off to take a break, are there any other questions on routing overall? No? OK. We'll take just a 3-minute break, and then Narek's going to come up.